Hello, hello, hello. Hopefully people can see me and hear me. How are we doing? How is everybody doing? Everyone feeling all right? Welcome to our first Sunday GCSE class, which is very exciting. How many have we got now? This must be, well, I've lost count now. But we've had lots of GCSE chemistry classes, which is great. Really exciting stuff. But this lesson, we're looking at Year 11 chemistry, or what most would consider to be Year 11 chemistry, which is exciting. We're taking a step forwards now, away from the basics, and looking at rates of reaction is our next step. So hello, 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 everybody. Well, welcome, welcome, welcome. Welcome if it's your first time. Welcome if you're coming back. It's nice to see that we've still got some familiar faces. I know Sunday's a bit of a different time to have a class, but I think it's quite a nice time, a nice relaxed time to have a class, I think, on a Sunday. So hello. I'm doing well, actually, thank you. Yeah, really good. Hi, hi, hi. So I'm not sure about live Sunday sessions. I haven't been involved in any conversations about that, but we definitely do them for A-level. I think it would be an exciting thing to do again. There would be some more YouTube sessions for GCSE. But this will be our last GCSE session before we move on to the website, unfortunately, or for a bit. It's the 11th class, is it? Oh, very nice. Wow, very good. I haven't been counting, I'm going to be honest. We'll just give it another 30 seconds, see if anybody else wants to arrive, and then we'll get going. Hopefully everybody's doing okay. If you haven't already, I think the link for the slides was sent in the chat, so please have a look there for the link. It is sometimes at the bottom as well in the chat. I'm just checking in the description, sorry, which it is. So please download the link to the slides from there as well. Because that is very useful for you guys. You can take them away with you, you can reuse them, you can redo the exam questions, you can scribble all over them now whilst we're going in class, so all really, really useful. So yeah, well, I mean, I will mention it, that would be great, but we'll see how we do, I guess, with our first week back on the website, back in our home, as it were. Okay, let's get started then, I think, because this is going to be quite a full class, but it's hopefully going to be quite an interesting class because it's one that we can use lots of modelling to think about, and we can apply to our everyday life and all that sort of thing. So although we are going to have to do, unfortunately, a little bit of imagining when we're talking about our practicals, because obviously I can't do a YouTube practical. Or I can't get you guys doing a YouTube practical anyway. So we're just going to have to look at the theory, unfortunately. So hello, hello, hello. Welcome everybody to this class. We are doing rates of reaction, which is a Year 11 topic usually. So it might be a little bit more advanced than some of you are used to from these classes, but it's still a lesson, so we can still interact. You can ask as many questions as you need, and hopefully I'll try and answer as many of them as possible. So a little bit about me. For those of you, I think some of you will be returning students, which is amazing, but if not, then this is a little bit about me. I am the lead GCSE chemistry teacher at Snapprovise. I have a PGCE in chemistry education from Oxford University, and I really enjoy teaching and tutoring A-level chemistry and A-level sciences and GCSE sciences, and I've been teaching A-level chemistry for the last 6 years, so it is something I very much enjoy doing. And just for those of you, again, if you're not sure, if you haven't come to one of our sessions before, we are going to be moving our GCSE tutoring, which we have been doing on YouTube, onto the website. So if this is something you're interested in carrying on doing, please go and have a look at the website, see if it's something that could be useful to you. It is multiple classes per week. I can't remember the exact number, but it's at least 3 classes per subject per week. So that's loads of subjects. We've got biology, physics, chemistry, and maths. So loads of classes for you to jump in on. There's lessons and there's drop-ins as well. We cover the full curriculum. We have these lovely high quality handouts that you can print, take home, or take away with you, scribble all over, do whatever you want with. And we have a library of past recordings, so every lesson is recorded and then you can watch it back. So if you miss a session, you can watch it back, or if you want to revise something, you can watch it back, or if you just want to go back over something because you missed that definition or you want to remember how to do that exam question again, you can watch it back again. So it's really useful resource for you there. And then there's also one-to-one support. So we are interactively responding and engaging with you guys. So it's all amazing stuff. And if you want to just try it out for 2 weeks for free, then please do. If you go to snaprevise.co.uk, enter your details and everything, and then on the checkout stage, you need to enter the code tutor14, and that gives you 2 weeks, 14 days free from the moment you activate it. So it's a really, really good opportunity for you guys to try SnapRevise and just see if it's something that you want to keep going, see if it's something that you are wanting to engage with. So, oh yes, there was a time, and I can't remember when it was. I think it's a week from, oh, I'm not sure. When does it expire? I want to say the 9th, but that feels too soon. There you go. It is midnight on Tuesday, the 9th of March. There we go. So yeah, Tuesday, the 9th of March, because I guess actually we have been using this code for a week or so now. So that does actually make sense. I'm not sure actually. Layli, does Tutor 14 also give 14 days for A-level resources? It definitely gives a free 2-week trial. And you can start already. Yes, you can, Annabella. Yeah, but the classes will start on Monday on the website. There you go. It gives you access to just the tutoring program. Okay, so this lesson then, guys. Oh, you go for both GCSE and A-level. So this lesson, we're going to look to understand what the rate of a reaction is, how do we calculate it, and the equations that are used to calculate it. We are going to describe, because unfortunately we can't do, but we're going to describe practicals that can be carried out to work out the rate of a reaction, and we're going to use graphs to determine the rate of a reaction. But things that we're not going to look at is collision theory or factors affecting the rate of a reaction, because that's coming in a later class or next class. So next, again, for those of you that have been here before and know what you're doing, you're old hands at this, we've provided you with the specification points. So if you're on AQA, OCR or edXL specifications, then you can just have a look. This is the content that for your exam board that we will be including in this practical, in this lesson, sorry. And so you keep an eye on it, double check that you're happy with everything you should know. And if there's any questions you've got, please ask me because we can chat through it together. Okie dokie. Oops, I can't move on. There we go. So what do we already know? You may or may not already know this, but if you are a year 11 student, you should hopefully know this. What do you get when you react a metal and an acid? What do you get when you react a metal and an acid? Does anybody know? Has anybody got any idea what's produced? If you've ever taken, if you've had the luck, if you've been lucky enough to be in a classroom and you've dripped some acid onto a metal, what do you see happening? Good, yeah, really good. Metal plus acid is salt and hydrogen. Nice one, well done, guys. It is a salt and hydrogen. So these are our reactants. And these, whoops, are our products. Brilliant. Is this for CAIE? Well, actually, the specification overlap. This is a question for Zanstanium. Sorry, I can't read. My screen's quite small. The specifications are very similar amongst them. We don't specifically include CIE in here. But if you got your specification up and found the bit on rates of reaction in the specification, you could double check if there is anything that's missing or if there's anything that we cover that you don't need to know. because a lot of the content, especially GCSE, is very similar between the exam boards. So it's likely that a lot of this is relevant if you want to stay. Brilliant, guys. Well done. This is awesome. Okay, and then a little bit of Key Stage 3 physics and maths. What's the equation for speed? How do we measure the speed of something? What's the equation that we need to know for speed? Anybody know? Good, distance over time, or if you're going to do velocity, displacement over time. Good, but because we're talking about speed, we should probably just put distance over time. And this is distance over time. This is, what's this an example of? This is an example of a rate. How far something is traveling per unit time or per second. It's how far something is traveling per second. So this is a rate, something, a quantity, in this case distance, over time, the time it takes for that to happen is a rate. And that's what we're looking at here. We're looking at rates. Good, well done. Very nice. So a little bit of intro then to rates of reactions. If we are looking at the rate of something, whether it's the rate of travel, i.e. speed, whether it's the rate of somebody's ability to eat sweets, whether it's the rate of your sister's ability to put basketballs in the hoop, whatever it is you're doing the rate of, we have to look at the change in a quantity. So I'm going to call it quantity A over, oh, I can't spell quantity apparently. Let's try that again. Quantity over the change in quantity B. And if it's the rate of something, it's usually our change in quantity A, especially if we're talking about the rate of a chemical reaction, this is usually, actually let's do this as separate ones. So this might be our change in amount of reactant or product, reactant or product over the change in time. So when we're looking at a rate of a reaction, we are looking at the change in the amount of a reactant or the amount of a product over the change in time. So yeah, brilliant. Well done, Samia. That's brilliant. It's either the reactant being used up or the product being formed. Brilliant. I was just about to say that. You beat me to it. Really good. Lovely. So we can describe the rate of a reaction as how fast a reaction takes place. Or the change in a reactant or a product. Or products over time. So we can think about it in two different ways. We can think about it in terms of a very definite, this is how long a reaction has taken place, or we can think about it as more of a moving thing. It's just the change in reactants or products. Oh, I did say over time there. It's obviously disappeared. Over time. Lovely. We're not actually going to talk about catalysts. That's the next lesson. I think it's the next lesson or one of the next lessons coming up. Whenever we do our next Year 11 lesson, we'll be looking at catalysts. Okay, so hopefully if anybody's got any questions, please ask them in the chat and I will try to keep an eye on it. But otherwise, can you give me quantities that we can measure a changing reactant or product in? If we want to measure the amount of reactant we've got, what quantities or what units can we be measuring them in? What are we looking to measure? We're not going to look at measuring them in apples. We're not going to look to measure them in spaceships. What are our measurement amounts going to be and what are our units therefore going to be? Brilliant, very good. So mass, I can see, has been written there and that would be measured in grams. Great. Could be measured in kilograms, potentially, if that's what your questions ask for, but grams is normal, and therefore our rate units would be grams per second, or grams over divided by second. What else have we got? Oh, nice. We've got a volume in there. Very good. We've actually got 2 now, and that could be measured in, and I really like the fact that you've said this, could be measured in centimeters cubed or decimeters cubed. That is very true. We can definitely measure them in decimeters cubed as well. So actually, let's put both of them in, just so that we don't get confused. And then whichever one we're using, it would be centimeters cubed per second, whoops, I put per gram, or decimeters cubed per second, depending on what we've been given, what we're wanting to use, what we need to use it for, etc. I saw somebody said moles, which is amazing. This is actually a higher tier thing, so you don't have to be able to use moles if you aren't doing higher tier. But if you are doing higher tier, then you do need to know about moles. So moles, which is another amount, which I'm not going to go into now, but it's a good thing to get your head around if you haven't yet. And the same, our rate units is going to be moles per second. And then finally, one which I don't think we've had yet, but when we're doing a practical in the lab, we often get things in concentrations. Who can tell me what the unit for concentration is? What is the unit for concentration? Does anybody know what the units are? Yeah, the units for concentration. It's not conc, unfortunately. We have to go back down to our SI or our standard units. Good, really nice. We're talking either grams per centimeters cubed or grams per decimeters cubed, or anything like that. Yeah, really good. So we're thinking grams per decimeters cubed. Actually, let's put centimeter cubed in first. Grams per centimeters cubed, or grams per decimeter cubed, because a concentration is a bit like a density. We want to know how much mass there is per volume. So grams per centimeter cubed. We can also talk about it in terms of moles per decimeter cubed or moles per centimeter cubed, but we're not going to go into that now. And therefore, our rate units have got to be grams per decimeter cubed per second. Whoops, I've written that wrong. Try again. Grams per decimeter cubed per second. Now this to the -3 you hopefully have met before, but it's the same as writing divided by per. So grams per decimeter cubed is the same as grams over decimeters cubed. So that's what that little minus sign means. Brilliant. On the first one, oh, that's supposed to say kilograms, but I've just, my pen's come off when it shouldn't have, but good spot. Well done. Thank you, Callie. Yeah, or mole per decimeter cube for a concentration as well. Yeah, great. Yeah, exactly. Very nice. Okay, so let's have a look. Concentration is, so you can measure its concentration. You can measure concentration in moles over volume. You can also measure concentration in mass over volume as well. Yeah, either works. Just depends what you're then using it for. And at GCSE level, we're probably going to stick to grams over volume just because it makes it easier than having to go into moles into that much detail, especially at this level anyway. Okay, so next bit then. So if we're trying to calculate the mean rate of a reaction, so we've looked at what those equations are that we need to use, or the equation that we need to use. Our rate is equal to our change in something over time. So what are we looking at our change in? What quantity, what thing is going to be changing in this case? So, and therefore, what calculation do we need to do? So you're right, concentrate. So yeah, that's it. Good, yeah. Our quantity of, or sorry, I should put change in quantity. Change in quantity which in this case, our reaction is 4 grams of magnesium reacts with an excess of hydrochloric acid, so loads of hydrochloric acid, we don't need to worry about it. The reaction takes 50 seconds to complete. What is the mean rate of this reaction? So you're exactly right. What we're looking for to change is this 4 grams of magnesium. That is what is going to be changing. Oh, I should put change in time as well. Change in time. And so in this case, our change in our quantity A is this 4 grams of magnesium. Once that's been used up, then our reaction will stop because there's no more magnesium to react with the acid. So once the magnesium's used up, our reaction stops. So how long is it going to take for that to happen? Well, we're going to wait and see how long it takes for our 4 grams of magnesium to be used up. So change in mass of our reactant in this case, which is magnesium, divided by the time it took for the reaction to happen. So in that case, if anyone can do the calculation for me, that would be brilliant. So our change in mass is going to be 4 grams divided by the time it took, which was 50 seconds. So 4 grams, thank you, you're brilliant, well done. 4 over 50 is 0.08. Fantastic. And our units, we must include our units, so it's grams per second, or GS to the -1 if you want to write it like that. Oh, Candy, limiting reactant. We won't be doing that in this exam, in this lesson, but it is a very good question, and it's something that students often struggle with. So, but that would involve looking at the moles of your reactants and working out which reactant has the fewest moles in a reacting ratio, and that's how we would find our limiting reactant. In fact, we did a question on it in the last drop-in. So if you after this, if you want to flick back through the YouTube and find our drop-in, I believe it's on there, if I'm remembering correctly. Okay, how is everybody feeling? That's our answer there. How is everyone feeling about, whoops, too far, about this? So let me know, how are you feeling? Yeah, this is easy, straightforward, fine. Or it's all right, it's fine, I'm keeping up, but you know, it's a bit challenging, or oh gosh, no, I'm super confused. So just let me know in the chat, 1, 2, or 3. We will be doing a little bit on graphs, but not a huge amount, because we'll be looking more about gradients of graphs and finding the rate, just because otherwise we will be a little bit short on time. Everyone's happy? Please let me know if you're not, or if you've got any questions. Otherwise, we will move on. So well done. So let's have a go at an exam question then. We've just done an example, an exam star question. Let's look at an actual one. So magnesium reacts with hydrochloric acid according to the following equation. Magnesium plus 2 lots of hydrochloric acid make magnesium chloride and hydrogen. So this is our salt and our hydrogen. So this is metal plus acid makes salt and hydrogen, just as we looked at the beginning. If 40 centimeters cubed of gas is produced in this reaction, the reaction takes 35 seconds to reach completion. Calculate the mean rate of this reaction to 2 significant figures, and we'll come to that again at the end of this bit. So how do we do this then, guys? We're looking again at the mean rate. So we're looking for the mean rate of this reaction. So we need to know the change in a quantity divided by the time the change took, or the change in time, I could have said actually. Let's put that so I'm being consistent. Change in time. So our change in quantity, what's happened? Yeah, good, guys. Really good. So in this case, it's our volume of product that's formed that we need to use. And in this case, it's 40 centimeters cubed. So our rate, oops, I didn't finish that, 40 centimeters cubed divided by the time it took for that product to be formed, which in this case was 35 seconds. Don't know why I'm incapable of writing on the lines today. Who knows? So who can do that for me? Do you get marks for writing the question? Great question. For writing the equation. Great question. no, actually. Or, well, yes and no. So if I get my green pen out, or let me just write the answer in. So it's 1.14 something, 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 something. But in centimeters per second, I keep writing grams, centimeters per second. So if we're writing it to two significant figures, we have to round our third significant figure, or our third figure, we have to round. So in that case, it's just 1.1 centimeters cubed, because 4 rounds down. So to answer your question, where do we get marks in here? So actually, technically, you would get 1 mark for writing the equation, probably with the numbers in, and then 1 mark for your final answer to get the 2 marks. However, if this equation was wrong, or you did it the wrong way round, or you put the numbers in wrong, you may be able to, and therefore you wouldn't get the answer right either, you may be able to pick up an answer, a mark for writing the equation. So if your examiner can see you knew what you're supposed to be doing, you just made a mistake, or you used the wrong numbers, or you plugged something weird into your calculator, you could still pick up a mark for writing the equation, because you're showing your examiner you know what you're supposed to be doing. There was just a mistake made afterwards, so you'd only lose the 1 mark in that case. However, obviously it's better just to not make a mistake if you can help it. And if you're running slow on time, or running low on time even, then it's not worth writing the equation, because you'd get the mark for writing it with the numbers in, with the right numbers in. Hope that answers your question. Okie dokie. So let's have a look at the next bit, part 2. If anybody's got any questions, please let me know. But otherwise, part 2, we're going to look at the practicals. Now, unfortunately, because again, you guys can't be doing the practicals at the same time, and I don't even have the equipment to do it, we're just going to have to talk through them. So in this practical, we've looked at, again, it's our metal plus acid makes salt and hydrogen again. So it's the same equation, or same chemistry that we're looking at. And so in this case, hopefully you can see this will be my magnesium strip. So my metal strip, and it's inside my acid, my HCl, hydrochloric acid. And actually we can also call that a ribbon as well, magnesium ribbon. Magnesium ribbon. So how do we know then when the reaction's finished? Visually, if you were in a lab and you had your conical flask with your magnesium strip in some acid and it's bubbling away, you can see the bubbles being produced. This is the H2 gas being produced. That's what the bubbles are. It's bubbles of H2 gas. Bubbles of H2 in the gaseous state. I should probably put gaseous H2. So if it's bubbles of gaseous H2 being produced, how do we know when the reaction's finished? What are we going to observe? Yeah, brilliant, guys. Awesome. The bubbles are going to stop. So what we can do is we can work out how long the whole practical, or the whole reaction took by timing how long it takes for the bubbles to stop. And as soon as they've stopped, you stop your stopwatch, because we always have to use stopwatches for this. And we wait until the fizzing has stopped. Once the fizzing has stopped, that is our reaction finished. So that means that actually, if we're not calculating the change in a product or the change in a reactant, then the whole reaction, we can work out how long the whole reaction took, or the rate of the reaction, by just doing 1 over the time it took in seconds, or whatever we want to use. So we can tell that the mean rate is proportional to, that's what that little symbol means. It means it's proportional to. So we do this by measuring the time it takes for the reaction to finish. Oops. Oh, that hasn't arrived, then appeared. Time it takes for the reaction to finish. Oh, I ran out of space there. Finish. There we go. Okay, can't see that there. Okay, anybody got any questions? Yeah, good. And I love the use of the word effervescence. That's brilliant. That's a really good word. But at GCSE, you don't have to use the word effervescence. You can, they will allow bubbles or fizzing, but effervescence is amazing if you can use that as a word in this. Ah, brilliant. We are just about to move that on, which is move on to that, guys. So you are all on the right wavelength. You're on my wavelength, which is great. We can also, however, measure how the rate changes if we want to through a reaction by measuring the production of our product over time. And we would do that, as you guys have said, which is great, by using a gas syringe. And that's what this funky looking thing is here. It's a gas syringe. And we have to, obviously, bung it up. Why do we need to put a bung in? Why does this have to be bunged here? Why do we need to be really careful, actually, about keeping the bung in place on our conical flask? What do we reckon? Why does this have to be a sealed system? Good, really good, yeah, so that we don't have any escaping gases, or because otherwise our results would be inaccurate. And again, we've got our magnesium ribbon and our hydrochloric acid. And then again, we've got bubbles, but this time our H2 gas is going to be collected in the gas syringe, and then we can read off to see at certain periods of time how much gas has been collected. So in this case, when we're doing this, anybody know what the equation is going to be? What's our mean rate going to be here? We've been looking at it quite carefully in previous slides. What's the equation? Anybody know? It's going to be in exactly the same equation that we've been using previously. It'll be the volume of our product produced or product formed. Oh no, sorry, I must have been pressing that with my sleeve. Go back, go back, go back. Volume of product formed divided by the time that it took to form. And we can do that regularly over time. Yeah, brilliant, well done. Exactly right. We can do that multiple times, which we'll look at in a minute, or a couple of minutes actually, in order to plot a lovely graph. So this is a good one. This setup is a good one for looking at graphs, being able to compare the rate over time or see how the rate has changed over time. Whereas if we go back to the previous one, you get one number. You get how long the whole reaction took for this one. So you only ever get one number. You get the mean rate. But if we do it over a period of, if we do it in a continuous monitoring method, that's what these are called. If we do it continually, then we can get some data that we can put into a graph. The other way we can do it, we have just looked at our collecting the gas that's produced. But the other way we can look at is using up the product. So we can look at using up the reactants, or the escape of products, the production of products and their escape. So there's some different ways we can do it. With this practical, which again, if you're lucky enough to have had the chance to do, is you put some calcium carbonate in the bottom, you add it to an acid, and in this case, we get our metal carbonate. Anyone know the general reaction for this? Metal carbonate plus acid, and there's a hint just above. What's produced in this reaction? Metal carbonate plus acid makes what? Anybody know? Anyone know what the general reaction is for this? Good. Yeah, well done. Our salt. Don't forget our salt. I've done my arrow a little bit further over. Don't forget our salt plus water plus carbon dioxide. Good. Okay, so in this case, because carbon dioxide gas is being given off and we haven't bunged it up, we are allowing it to escape because this is just cotton wool. That's to stop lots of things splashing, but it's to allow gas to escape through it. So if the carbon dioxide is allowed to escape, then this is going to get lighter because carbon dioxide, which has mass, is leaving. And as it leaves, our solution, our reaction mixture is going to get lighter. And so we can measure the change or decrease in mass of this reaction over the time, again, it takes for this mass to leave. So every 5 seconds, for example, we can measure the mass, and eventually we can plot it into a graph and we can see how the rate is changing again. Good, well done. Okay, and the other thing we could look at, just for those of you doing in higher tier, what we can do is look at the moles of the product formed. So we can do the rate. This is slightly separate. We can work out the rate, using the moles of product formed over time, and how long that is taken for those moles to be formed. Oh, the cotton wool, is just to keep because it's going to be bubbling quite a bit, we don't want it to splash out, because if it splashes out, then some of the HCl droplets might leave, and that will change our mass, but not correctly. So we don't want any HCl to leave, or anything that isn't carbon dioxide. We only want carbon dioxide to leave. So it can leave through cotton wool, because cotton wool is not solid, or not a solid. So it's just to stop splashes and to protect your hands. You don't really want to get concentrated HCl on you. And so it is a conical, oh dear, I can't spell conical flask, and then this is our balance. You can also call it weighing scales, but we should really call it a balance. Okay. Lovely. Yeah, very nice. Well done. Yeah. So we can do, you can use your mass moles MR to work out what your moles are as well. Yeah, good. But again, like I said, I'm not going to go into this because we don't have time in this lesson. We need to focus on our rates of reaction. How are we doing for time? Not too badly. Okay, so next, or final, practical that we're going to look at today. If you've got a specific question, Yara, I can go back. So if there's something that you are specifically worried about, but otherwise this one is quite a fun reaction, this one, especially if you get the chance to do it in class. But we can look at this is called, well, sometimes it's called an iodine clock reaction, but we can look at the time it takes for sodium thiosulfate to react with hydrochloric acid. And it produces this sulfur, and sulfur can turn this cloudy yellow-white precipitate, it turns into a solid in the reaction. And when it does that, it covers up the cross. So when we're doing these kind of reactions, what we're looking at is we're looking to measure the time taken for the cross to disappear. I mean, it doesn't have to be a cross. You could do yourself a smiley face if you want, but you just need to have an accurate endpoint, and the endpoint is usually when you can no longer see whatever is underneath your conical flask. It's normally how long it takes for the cross to disappear. Well, that's one way that we can do it. So we wait until it's gone completely non-see-through. So when you're looking, this is my picture of an eye. So if you're looking down over your conical flask, you can no longer see the cross. Yeah, lovely, really good. You don't need to know the equation for this, don't worry, we're not going to waste time on this, but it is sodium thiosulfate in the beaker. Oops, not beaker, in the conical flask, sorry. Let's label that as a conical flask. And then this is a cross drawn on the paper. So it's sodium thiosulfate, which starts transparent or see-through, and then a precipitate, a solid, will appear out of the solution, or will be formed in the solution. It means you can no longer see the cross. The other way we can do it, which you guys again probably haven't had the opportunity to do, especially because it does need specialist equipment, but we can measure our color changes changes, not changer, changes using a colorimeter, which is a technical piece of equipment whose job it is to measure kind of the light traveling through substances to see what kind of how much light it can travel through our substances. So we can look at the color change using a colorimeter. Right, what questions have we got? Yeah, very good. Precipitate is the insoluble product made. Yeah, good. Yeah, product is what you get. You get the sodium, you'll get a sulfur precipitate formed, and then so it's sodium thiosulfate and hydrochloric acid, I think. Okay, lovely. Okay, let's see how everyone's doing, because I'm just aware we're running a little bit shorter in time. How is everybody? Everyone, how's everyone feeling? Just let me know that if you're feeling fairly happy with it. It's okay, it's not brilliant, but I'm fine, I'm coping, or I'm super confused and I'll have to go back and watch this whole lesson again, sort of thing. How are we feeling? Please feel free to say whichever. That's absolutely fine. Lovely. Okay, no, that's absolutely fine. That is absolutely fine. So if we've got time at the end, we can answer individual questions as well. Having said that, I barely have time at the end because I always talk too much. So let's see. Let's see how quickly we might have to. We're going to skip this for now. If we have time at the end, we're going to come back to those exam questions. But I'm very aware we've got a whole section left to do and we've only got 15 minutes in which to do it. So, cool. So part 3, rates of reaction graphs. Now, rates of reaction graphs are only needed for, measuring gradient on rates of reaction graphs is only needed for certain parts of the specification. However, or certain parts of certain specifications. However, everybody has to know how to draw a graph. Everyone has to know how to represent this data on a graph, and everybody has to be able to read a graph of this sort of data. So, oh, Callie, good question. On the triangle page, we put MR, relative molecular mass, that is. So that's calculating how many protons and neutrons there are in an atom using the periodic table. It's not something that I've done with us yet as a class, or we've done as a class, but it is something that hopefully you will meet at some point soon. It's not that difficult to do. It's just once you've got the practice, once you've got into the habit, once you've practiced it, it's a lot easier. Okay, so when we're doing rate graphs, from according to change in the quantity of a reactant or product over time, we can plot a graph. So if we look every 10 seconds, we have taken a measurement of a volume of a gas in centimeters cubed, and we've plotted it on a graph. What I'm going to do is back the other way. I'm just going to fill in these volumes of gases from the graph because it's something that we need to be able to do. And this, in this case, our volume of gas is our product because it's being produced. And we can tell it's being produced because the amount of our gas is increasing. So we know this has to be a product because it's being produced. The amount is increasing as time goes on. So in this case, at 0, there is 0. I'm going to need to rub out my line, aren't I? At 10 seconds, we are at about 24. At 20 seconds, about 36. At 30 seconds, about 43. 30 seconds, yeah, about 43. At 40 seconds, 2, 4, 6, 46. At 50 seconds, we're leveling off. So what's that? 49, probably. And then fine. Oh no, not 49. I can't read a graph. That's good. 47, I mean. And then at 60 seconds, we're still at about 47. So hopefully we can see using this, or can you tell me at what point does the reaction stop, or has the reaction stopped? At what time has this reaction stopped? Well, we're going to look at measuring the gradients of a graph in a second. So it's a good question. Anybody know how many seconds on this graph, or at what point has the reaction stopped? Have we stopped producing any product, so the reaction has finished? Good, it is at 50. At this point, there's no change in product. So at this point, our reaction has stopped or finished. Very good, well done. If they ask you to plot a graph and it curves, do you do a line of best fit or do you join the points? If it's continuous data, so like time is continuous data, then you would draw a curve, usually. And if you're ever not sure, I would draw a curve. It's more likely to be a curve than joining the dots. Well done, those of you who said 50 seconds, that's great. So when we're looking at rate graphs and rate, if we look, the gradient of the beginning of the graph is a lot steeper than the gradient at 40 seconds, let's say. And we can look at this by drawing what's called a tangent. So these are tangents here. So if we draw a tangent, then we can look at the gradient of that tangent and work out what the rate is. So the steeper the tangent, what do you think that says about the rate? My pleasure. What do we think that says about the rate? The steeper the tangent, the faster the rate or the slower the rate? Good, brilliant, well done, exactly right. So the steeper the tangent, the faster the rate, or the larger the rate, you could say. Good, well done. And therefore the rate in this case is greatest at the beginning or the start of the reaction, as you say, because we've got everything in really high concentrations. But we're not going to look at that this lesson, that's next lesson. But you're exactly right, it's greatest at the start because that is the steepest tangent. At 50 seconds, as we said before, the reaction is over because it is no longer producing any product. There is a flat tangent. Fan-dabby-dozy, well done. Good. Okay, so this bit, everyone in OCR, this next bit, everyone in OCR has to be able to do, but only higher students for AQA and EdXL. And this is determining the rate using a graph. So this is calculating or working out what the gradient of these curves are. So when we're doing our rate, we're looking at the change in a quantity over the change in time. And so in this case, it's going to be the change in the product volume, I should say, the volume of the product over the change in time. And if we look at a graph, that means if we've plotted the volume and we've plotted time, we've plotted volume on the y-axis and time on the x-axis. So we're actually doing the change in y over the change in x. When we've plotted it like this, when we've plotted time on the x-axis and volume of gas on the y-axis, we're doing change in y over change in x when we're trying to calculate rate. And so that is our gradient. So change in y over change in x equals the gradient. It is the gradient. And to do that, then we can do a point, y1 minus a point on y2 over x1 minus x2. To see how it has changed. Actually, I should probably do it the other way around. Let's do 2 minus 1, just to encourage us to do it that way around. And that is equal to our gradient as well. Gradient. That should be an E. Gradient. Okay, how are we all doing? Good. How are we doing for time? Not too bad. Okay, we're going to speed through this next bit then. So let's actually do a question. Let's do a practical. Yeah, there we go. Samir, we're just doing an example now. See, we're on the same wavelength. So we're determining the rate then. We've got an example. So when magnesium reacts with hydrochloric acid, hydrogen gas is formed. So in this case, that's our volume of our gas being produced is hydrogen gas. And the graph below shows the production of hydrogen gas, the hydrogen gas being formed in this reaction. What is the rate of the reaction at 22 seconds? Now, in order to do this, we have to draw a tangent. So we have to draw a tangent at 22 seconds, and that's harder than it sounds. Now, in an exam, if you have to draw a tangent, they'll have a little bit of leeway. They will be nice to you and allow you to get it a little bit wrong because it is a hard thing for you guys to do, for anybody to do. So just looking at 22 seconds, so that's here. So I want to try and draw a tangent that is approximately, if I can, along the line or the steepness of the line at this point. So we're looking for it to be sort of, and this is not a very straight line because I haven't got a ruler, so hopefully you guys would do it with a ruler, sort of along there. Now I have curved a little bit at the bottom. So let's try and do that a little bit less curved. Okay, something like that. We'll try something like that. So if we want to do a gradient, we want to do change in y over change in x. So let's read off 2 points along our line, which I'm going to take as the biggest points I can, because that's the best way to get the most accurate answer, is to try and use the biggest numbers you can. So in this case, I'm going to be looking at the change in y here over the change in x here. So that means my rate equals change in y over change in x, which in this case is going to be, what have I done? 50 minus 0 over, what's that? 38 minus 0. So it's 50 divided by 38, which is, and I need to get my calculator out. $50 divided by 38 equals 1.3 centimeters cubed per second. 1.3 centimeters cubed per second. I'm going to write that out a bit better because that's not very good. Centimeters cubed divided by seconds. There we go. 1.3 centimeters cubed divided by seconds, or per second. So what I've done is I've drawn my tangent at the point on the graph. So this is where it equals 22 seconds. I've drawn my tangent and then I've done a gradient of the tangent. So, oh, you're right. Thank you for pointing that out. It's because I drew my thingy there. You're right. So I need to use that point and that point. Sorry, you are exactly right. Good spot. So 50 minus 20 over 38 minus 0. Yeah, it's because I drew my line and then I didn't pay attention. Good, great spot. Well done. This is why we need amazing people like you guys. So 50 minus 20 is 30. 30 divided by 38 is 0.78. 0.78 centimeters, or actually 79 really, 79 centimeters cubed per second. Great spot, well done. Really good. Everyone happy? Yeah, good. Really good, guys. Cool. Really nice. Well done. Okay, we are, I think, probably going to need to get ready to call that a day. There is another exam question, which is looking very similar to the one we've just done. So please feel free to have a go at that one. And apologies, what great spot for those of you that spotted I'd done the gradient wrong. That's really good, really, really good. Please feel free to have another go at this one in your own time. But just to remind everyone, hopefully now you are feeling a bit more confident about understanding what the rate of a reaction is and how we calculate it, and describing some of the practicals that you should be aware of that you can do to calculate the rate of a reaction, and using graphs to determine the rate of a reaction. So key points of these things. Has anybody got, we've got about a minute, I think, for questions. Has anybody got a question that I can answer briefly? Oh, hello, Marianne. There should be, yes, there should be a web class 6 till 7, and then I'll be doing the drop-in 7 till 8. Yeah. Good. What affects the rate of reactions? Great question, but that is actually something we're going to do in the next, or the lesson after this one is looking at factors that affect the rate. So what can affect it? So between now and then, if you want to come and join us on SnapRevise, please have a think about what you think could affect the rate of reaction, and we can see if you were right. How does the particle theory relate? It does very, very, they are very interlinked, particle theory and rate of reaction. So yeah, very good. Okay. Sorry, Callie, what's the rate of, is what for GCSE or A-level? Is there a maths revision? Oh, I was under the impression there isn't, but I could be wrong. I'll be heading off in a second anyway, so they can take over if they need. Are the SnapRevise live streams still going to continue? Not yet. I mean, there's, I think, the option in the future, but for the odd live class, but it's at the moment we are just going to take GCSE onto the website. There are still the A-level live streams every Sunday, but not GCSE at the moment. Is that for GCSE or A-level, the online videos for today? Oh, I'm not. Oh, that's A-level, I'm afraid. Okay, right, I'm just going to have to do this final bit and then I will answer those final questions. So if you would like to join us on SnapRevise on the website, then please have a look, because we do have all this amazing tutoring available. We have loads of classes every week for biology, chemistry, physics and maths. We cover the full curriculum, so you can make sure that you've covered everything and had lots of questions answered about everything on the course. We have high quality handouts that you could take away with you and use to revise or check your knowledge. We record all of our sessions so you can rewatch them at your leisure as many times as you want. And there's also one-to-one support available so that you can get your personal questions answered. Okay, brilliant. I'm so glad to have been useful. And so if this is something you're interested in, please use this code tutor14. And you need to put it in at the checkout as you check out, and it should give you 2 weeks free trial. But that code does expire on midnight on Tuesday, so you need to use it before then. But why don't you come and join us for 2 weeks, see if it's your kind of thing, if it's useful enough to you, which would be lovely to see you guys on there. And that's starting tomorrow. Okay, so have a lovely day or the rest of the day, and I will see you guys hopefully on the website, if not maybe on a live session at some point soon. But if you're part of the email list, then you should hopefully be told about those. So if not, get yourself on the email list and you can find out if and when anything like that is happening again. And I will hopefully see you guys soon. Okay? Have an amazing time, guys, and I will speak to you guys soon. Bye. Thank you very much. Bye, guys. Well done. See you guys soon.